Okay, welcome. I'm Dr. Morton, and this is class day 10. This semester it's the 14th of September, and this Friday we have our first logic design test. It'll be the first midterm. We'll have two midterms and a final. So I do want you to try and do well on this test, obviously. And so I'm going to work through another test. I'm going to keep this video relatively short. And I will send out an email. I'm planning tentatively to have a time late tomorrow night, like I think about 11 p.m. I'm going to do an online Zoom where I'll try and answer questions and kind of do a little more review for anybody that's missing. I will also I will also try and live Zoom my lecture on Friday morning at 11 p.m. to noon. And so if you want to log in for that Zoom, I'll try and send out that link. I'll hopefully remember to do that, and I'll hopefully be able to set that up in class. I may not be able to, so if it doesn't work out, I apologize in advance, but the room is very complicated, and I've had a lot of trouble getting the camera to work and the Zoom thing to set up correctly. It's just been a real mess. It's just super complicated. But anyway, all right, so let's take a quick look at the syllabus. So we'll do that, and then and then we'll do some other things. Okay, so the syllabus, here we are on September 14th. Review chapters 1 to 5. That's what's going to be on the exam, and and I'll post this video and you can review it. And also, I think there is a homework due. I think there's a homework due Friday, and I'm just going to switch it to Saturday. So, in fact, I'm going to pause the video right now and do that before I forget. Okay, I made that change, and so now your homework 5 is due Saturday at midnight, along with the quiz. And always go to the last page of the syllabus, and you can keep track. So instead of the 16th, that homework then will be due on Saturday, which is unusual. All the other homeworks are due on class days. This will be the only one due on a Saturday, and the quiz is also due on a Saturday, and it's quiz chapter 5, and so that'll complete everything. Do the quiz before though; that'll help you. So you should have all the quizzes done by well. You still have till Saturday to get this one done, but you should do it before the test. Okay. With that, let me close the syllabus, and then I'm gonna work through this test. And I don't think this is the one I've worked before. All right, so I'm just going to go through this and work back and forth. And so the first thing I'm going to do is talk about this. All right, and let me blow it up just a little bit more so you can see it really well. Yeah, that's good. All right, so you're designing a system to test switch handles by putting them in a press that keeps bending the handle from 0 degrees until it breaks or is bent 90 degrees without breaking. You measure the angle with a pot that gives a voltage from ground to 5 volts at 90 degrees, and it varies continuously and linearly over the range of 0 to 90 degrees. You plan to convert the voltage to a digital value with an A to D converter. You have to select the precision of the A to D converter so that you can have the desired precision for the test. Your boss wants it to read to 1/4 of a degree. Answer the questions below by circling the answer. So how many different things must you be able to represent with your digital value? Okay, so this is pretty straightforward. So you have to resolve 1/4 of a degree. So excluding the fact that there may be some noise in the analog sensors and all that, we need to break this 0 to 90 degrees into 1/4 degree. So that basically means 4 times 90 are 360. And then since we're going 0 to 90, we have a beginning and an end. We have to add at least 1 to that. So we have to account for the 0 position as well. So that's actually going to be 361 things. Okay, so nearest power of 2 to 3. Well, so how many different things must you represent? 361. Okay, so that's the right answer for that. how many bits must your A to D converter have? Well, if you're going to resolve 361 things, then you take the log base 2 of 361 and round up to the nearest whole number. And it's easier just to know the powers of 2. So we know that 256 is too small, and that would be 8 bits. 9 bits is 512, and that would be more than enough. And so you have to go to 9 bits. So how many bits must your A to D converter have? Oh, that's interesting. I didn't give you an option there for the right answer. Let me just look at this a second. Okay, I fixed it. So you need 9 bits. You need 512 things to cover 361 things. And so you have a little better precision than a quarter degree, and should make your boss happy. If you go to 8 bits, though, you won't have a quarter degree precision, so that's not going to keep your boss happy. Is this device's sensor considered analog or digital? Well, it is considered analog because it gives you a voltage that varies continuously from 0 to 5 volts, covering the range of 0 to 90 degrees. And so it's clearly analog. Your A to D converter is going to convert that voltage with a precision of, it's going to put it in one of 512 bins. And that will give you the ability to be better than a quarter of a degree, assuming that the sensor's perfect, the sensor's good enough to that level of precision. So you'll get that value, but whether or not it really gives you that precision is up to how accurately the sensor is converting the voltage. But it basically says the sensor does a pretty good job of that, apparently. All right. Is this device sensor considered analog or digital? Well, it is analog. And then you're going to take the analog signal and digitize it in your microprocessor, or you're going to have a separate chip that's going to do it, whatever. What kind of code could be used to make the calculations easier in assembly? So if you were just going to use assembly, then, this isn't a great question, but the answer I'm looking for there is BCD. And remember, I talked about how in the early days we used BCD to do simple calculations in assembly language. And that's true. Doesn't apply perfectly well to this situation. You could just as well do a lookup table with 512 entries, each one representing a degree, and that would be another way to figure the value. Or you could do an equation. But if you did an equation, it's going to involve multiplication and division, and the BCD is not particularly good for that, so it's not going to really help you. So it's a bad question. But in any event, it'd be much better to do those calculations in C, a whole lot easier. It's really hard to do them in assembly language. All right. If the A to D has extra bits, does this affect precision or accuracy or both? Well, so if let's say you had a 16-bit A to D, well, it should give you better precision, but again, it really depends on how precise your actual analog voltage is. And if it's really precise, if it's precise enough that 16 bits works, that's fine. You will have much greater precision, and assuming that there's not a built-in error, you should have greater accuracy. So I think the answer here would be both. All right, now we're going to do this math, decimal 47. So how do you switch it to binary and hex? Okay, let's do this real quickly. I don't want to spend a lot of time on this. At home, you can use your calculator, so really, how tough is this going to be? But it could be a little tricky on the fractional parts. All right, so here we are. So I'm going to write this down, and I think you should be able to see this. Okay, so 47. So 47, we just divide by the base 2 in this case because we're going to binary, and we're also going to hex, but we're going to go from binary to hex and not from decimal to hex. So 47 divided by 2 is 13 with a remainder of 1. 13 divided by 2 is 6 with a remainder of 1. 6 divided by 2 is 3 with a remainder of 1. 3 divided by 2 is 1 with a remainder of, this is a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. And 1 divided by 2 is 0 with a remainder of 1. So our final value is 1, 1, 0, 1, 1. Notice low order, high order. All right. And let's check it. So this is 1 plus 2, not a 4, an 8, and a 16. So 2 and 8 is 10, 16 is 26, and 1 is, 10, yeah, 26, 27. So something's wrong. It's not 13. It's, golly, terrible. It's 23. Okay. So 2 into 23 is 11. Yeah. 2 into 23 is 11, remainder 1. And then 2 into 11 is 5, remainder 1. 2 into 5 is 2, remainder 1. 2 into 2 is 1, remainder 0, and 2 into 1 is 0, remainder 1. So this is now the high. So it should be 1, 1, 1, 1, 0, 1. Okay, now let's check it. 1 plus 2 plus 4 plus 8 plus, so 1, 2, 4, 8, 16. So not a 16 because you have a 0 there, but 32. 32. So 2 and 8 is 10. 42, 46, 47. 47. So it checks. All right. So the correct answer is 1, 0, 1, 1, 1, 1. Now, if we were going to convert that to 2's complement, the first thing you notice, it would already be negative in 2's complement, so obviously it does not fit in 6 bits. You'd have to pad out to 8 bits, or at least 7, if not 8 bits, and then you could convert it. And the way you would convert that is 0, 0, 1, 0, 1, 1, 1, 1. You copy bits so you get to the first 1, copy that, and flip everything else, so that would be 1, 0, 0, 0, 1, 0, 1, 1. And that equals negative 47, and this equals positive 47. 2's complement in 8 bits. Remember, always remember, you have to do it in 8 bits. But you always have to keep track of the number of bits. All right, don't ever forget that. Now let's switch it to hex. So I'm going to put the decimal point, count 1, 2, oh, sorry, not that. I want to do the binary. 0, 0, 1, 0, 1, 1, 1, 1. We'll put the point there, go 1, 2, 3, 4, 1, 2, 3, 4. So that's 2, and that's F. So in hex, it's going to be base 16, it's 2F. In binary, it's 0, 0, 1, 0, 1, 1, 1, 1. And in decimal, it's 47. All right. Then we're going to do 3B.8. All right, so this is not too difficult. All we have to do is just remember. So let's we'll switch this over. Okay, so 3B.8. So 3B.8. All right, so we'll deal with the decimal fraction in a minute. So I'm not actually going to do the math with. I'm not going to multiply by 16. Well, I am. So this is 16 to the 0, or 1. So B equals 11, and 3 times 16. So 3 times 16, 3 times 6 is 18. Put on your 8, carry your 1. 3 times 1 is 3, and 3 times 1 is 3, and 1 plus 1 is 4. So it's 48. So it's 11. 48 plus 11. So that's 9. So that's 59 point, and then it's going to be 8/16, or 1/2, or 0.5. So that's 59.5. And then in binary, we just write this out. It's really easy. In binary, we know that we're just going to do from the point 8 is going to be 1, 0, 0, 0. B is going to be 1, 0, 1, 1, and 3 is going to be 0, 0, 1, 1. So that's our binary. Base 2, that's base 16, and base 10. Sorry, I couldn't quite see the bottom. Okay, 59.5 in base 10, 3B.8 in base 16, and 001110111.1000 in base 2. Of course, you can drop these if you want. It's fine. Okay. All right. Let's see. So subtraction and multiplication. So let's do the subtraction next. All right, so I'm going to write that down. It's 11000 101. 11000.101, and then we're going to subtract 1011. 1011. So 1011.110. All right, 0 from 1 is 1. 1 from 1 can't do it, so you put a 0 there and put a 2 there. 1 from 2 is 1. 1 from 0 you can't do it, so you take this, put a 0 there. You'd put a 2 there, but you take 1 from that, so then you wind up with a 1 here and a 2 here. But that's a 1, 2 here, but that's a 1 and a 2 here. 1 from that 2 is 1. 1 from 1 is 0. 1 from 1 is 0. 0 from 1 is 1. 1 from, you don't have it, so you take that, you put a 0 and a 2 up there. 1 from 2 is 1. So that's the answer. 1100.111. All right. And then the multiplication, super easy. You just take the add in and write it in twice. Let's see, since that is 00011 times 1001. So that's easy. I'm just gonna. So it's going to be. I'm just going to write 11 and times 1001 times 1001. So I have a 1 here, so I copy the 1. I have a 0, so I copy 2 zeros. Another 0, copy 2 zeros, shifting left each time, and then finally 1. Now I add them up. 1 1 0 1 1. So the answer is So the answer is 11011. Okay? All right. And then, so let's see over here. Convert 59 to an 8-bit 2's complement number. All right, so let's first convert 59. All right, so I'm going to do that just like I did the other one. So I'll try and get this correct. So 59 divided by 2. So if it's 60, it'd be 30, but it's not, so it should be 29. And remainder 1. 2 into 29 should be 14. Remainder 1. 2 into 14 7. Remainder 0. 2 into 7 is 3. Remainder 1. 2 into 3 was 1. Remainder 1. 2 into 1 is 0. Remainder 1. So it's going to be low and the high. So it's going to be 1 1 0 1 1 1. Let's check it. So 1 plus 2, 4, 8, 16, 32. So 8 and 32 is 40, 56, plus 3, 59. So that checks. So this is 59. Oops, I'm right on the other page. So now, that equals 59 in decimal. This is base 2. So what we want to do now, pad it out. 1, 2, 3, 4, 5, 6, 7. Pad it out to 8 bits. So 0, 1, 1, 1, 1, 0, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. And when you pad it out to 8 bits, it's positive, so that's good. It should fit. 59 should fit. Remember, 8 bits goes from minus 128 to plus 127. Those are the biggest numbers you can use and the smallest. 59 fits into that, so we should be good. And so that's great. And so now we want to do the 2's complement. So we're going to invert every bit and add 1, or we're going to copy 1 so we get to the first one, copy that, and switch every bit after that. So I'll copy this 1, and then I'll switch 1, 0, 0, 0, 0, 1. And that's it. This equals minus 59 in 2's complement, and this equals plus 59 in 2's complement, or in unsigned, for that matter. Okay? Everybody happy, hopefully. Okay. All right. Okay, that's that. All right, moving along. I'm not going to work through that. Well, maybe I will. Okay. I'll work through this on in the chart here. So here we, oh, this is crazy. So I should have had, so these obviously have to be A, B, and C. All right. So A prime B. Okay. So for here, A prime would be 1 for these first 4 rows and 0 for these. So obviously these are going to be zeros because the A's are all 1s here. So, and then B has to be 1. So we're going to have 1s here and then 0s here. All right. For AC, then we have 0s for all these, obviously. And then we have a 0 here, but C is 1 there, so it's a 1. And then we have a 0 here, and then we have a 1 there. And then A prime, C prime. So again, the first 4 could possibly be, so the first one would actually be a 1, because A is 0 and C is 0, so A prime is 1 and C is 1, so that it would be a 1. And then the next one would be a 0, because C is 1 there. So that's, but the next one would also be a 1, and the next one would be a 0, as the rest of them would be 2. Now, A prime or C, well, so these are going to be 1, and then the C is going to be a 0 there, but a 1 there, and a 0 there, but a 1 there. And then here we have A plus B plus C prime. Okay, A or B or C prime. So this would be a C prime. So that would be a 1 because C is a 0. This would be a 0. C only 1, I think. And then here B is 1, so that's a 1. Here B is 1, so that's a 1. And then here here A is 1 for all these, so that's going to be a 1. Okay. Now you want to OR all these together. So any one in this group of 1, 2, 3, any one in these rows here is going to give us a 1 here. So we have a 1 there, that's fine. We have no 1s there, so that's a 0. We have a 1 there, a 1 there, a 0 there, a 1 there, a 1, oops, that is a 0. And the last one's a 1, right? Yeah. Okay, and then how about this? These both have to be 1. Both have to be 1. All right, so they both are 1 here, but they're a 0 there. They're sorry. And then here, they're both 1, so that's a 1. Here they're both 1, 0, 1, 0, 1. All right, let's look. 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1. Son of a gun. It is exactly correct. So it proves this relationship. Okay? So it's right. Explain how this proves the theorem. For all possible values of all the variables, the left-hand side always reduces to the same number, to the same 1 or 0 as the left-hand side. So it must be true. De Morgan's laws, let's do this real quickly. So this is going to be x or y inverted. So that's going to be x prime y prime. Oops. X prime y prime. And then this is going to be, invert this, we're going to get x plus y, right? And here, so this is, let me just write this out, it's a little easier. Oh, sorry, dang it, I didn't switch. Okay, did I do that whole thing and I didn't switch back? Oh, man. Yeah, it's hard to fix this too. I can't really edit these very easily. Okay, let me go back. Okay. So here's, so I went through this, but you couldn't see it. I recognize that now. So, so I had these, change these to ABC, and then we have, so this is A not B. Well, so A is 1, but B is 0, so that's 0. A is 1, but B is A prime is 1, but B is 0, so that's 0. A prime is 1, but B is 0, so that's 0. A prime is 1 and B is 1, that's 1. A prime is 1 and B is 1, that's 1. And then A prime is 0 for all these, so that's the end of it. AC, 0, A is 0 for the first 4 rows, and then A is 1 for the next 4, but B is 0 here, 1 here, 0 here, 1 there. And then, I did that wrong? Yeah, no, that's AC, my bad. That's AC, right, that's correct. And then A prime, C prime, so they're both 0, so that's a 1. C is a 1, so that's a 0. They're both 0, so that's a 1. C is a 1, so that's 0. And A is a 1, so those are all zeros. And then A prime or C gives us this. A or B or C prime gives us this. And then if we do these three, A prime B, AC, A prime C prime, then we get a 1 here. If any of these are a 1, we get a 1. So we get a 1 here. We get a 0 there because all three are 0. So we're looking at this group there. So we get a 1 there, a 0 here, a 1 there, a 1 there, a 0 there, a 1 there, and a 0 there, and a 1 there. And then for here, we're looking at these two, and they have to both be 1. So you get a 1 there, a 0 here, a 1, a 1, a 0, a 1, a 0, and a 1. And son of a gun, the left hand side and the right hand side are identical for all possible values. Okay? And then I went through these. X plus y, quantity inverted, gives us x prime, y prime. And then x prime, y prime inverted gives us x plus y. And then this one, w prime x plus y plus z prime, all inverted. Let's work that out on the paper. Okay. Just drives me crazy when I forget to switch it over. But it happens. Okay. All right. So I'm going to write that down. W prime x plus y plus z, I think, prime, yeah, and everything inverted. Okay, so when we invert this, we have to put in parentheses here or we're going to mess it up. So we do that, and we do w prime x, and we'll invert that. We'll change this to a times y prime. We'll change that to a times, and we'll get z non-prime. And then we'll take this inside here, and we'll get w plus x prime. So we switch that prime out, we bring a prime on the x, and we change the times to a plus. And then we keep the parentheses, because otherwise we'll get the wrong answer. And that's it. Okay. So let's look at this. SOP. A plus D quantity times B prime plus C times B plus D. Now, in this particular case, we don't have a good solution here. We don't have the same variable in every term or anything like that, and we couldn't really do much simplification. So probably the best thing to do here is to do the M and F on these two parts right here. So let's do that first. So we'll write it out and we'll do this. Okay, so it's just going to be A plus D, B prime plus C, and B plus D. So let's do M and F on just these parts. Okay, so that's going to be B prime D plus BC quantity times A plus D. Now, okay, now what do we do? Okay, so here's what we have. And again, we did the M and F on this, and that gave us B prime D plus BC multiplied by A plus D. Okay, so we did that. At this point, there's really not much else to do but multiply it out. So we're going to do A B prime D plus A B C plus B prime D D plus B C D. Now B prime D D just goes to B prime D because you don't need both of these, and the B prime D also shows up here, so this term goes away, so we're left with ABC, B prime D, and BCD. So it looks like this: ABC plus B prime D plus BCD. And so because you have a D and a D here, you can get rid of this B, and that gives you ABC plus B prime D plus CD. And that's the answer. Now, this is a hard one. This is level 2. I won't ask you a level 2. I'll try and avoid that. That's my intent anyway. There's only one that's even a little bit hard, I think, on the test. So maybe a 1.5 level. But that's a hard one. Yeah, it's a little frustrating. And seeing that you can get rid of that D, again, that's the eliminate the literal, which is I believe that's S2. Let's see. Let me just check this real quick. I do eliminate literal. Yeah, it's S2. So yeah, I didn't really mean to do this one. I did mean to actually. Okay. All right. So that's that one. Let's switch back here. Okay. So draw the logic diagram for this one. Make sure to get 3 layers. Okay. So let's look at that. This was actually a little tricky too. All right. So let me copy this down. So we'll switch out here. All right, x plus y times z, well, I'll put z over here, z plus, oh, okay, plus, yeah. Okay, x plus y times z plus wxy plus zw equals that. Okay, now first of all, it's not in pure form, right? We've got this OR gate here, so we don't want that. So I'm just going to take the z in here, and I'll get zx plus zy plus wxy plus zw. Okay? Now my wxy, yeah, so that's kind of interesting. So the first thing I'll do is I'll group these 3 terms and factor out the z. So I'll have zx plus zy plus zw plus wxy. Take out the z times x plus y plus w plus wxy. All right, so that's kind of crazy. So the first thing I'm going to do is I'm going to let this be x, this be z, and this be y, and use the second distributive law. So now I'm going to have x or wxy plus z quantity times wxy plus x plus y plus w times that. Well, so wxy plus x plus y plus w, well, this term goes away, right? Let's see. Yes, that term goes away. And now we have wxy plus z quantity times x plus y plus w. All right. So, yeah. So now, so this is kind of interesting. So what are we going to do with this? Well, so I guess we'll just multiply it out. Let's see. Well, actually we don't. So we have this in. So this is a fine SOP term, a POS term. So what we want to do is switch this to POS terms, and we know that that's going to be z plus W using the second distributive law, Z plus X, Z plus Y, and all that by X plus Y plus W. Now, yeah, so we have, yeah. So that's what it looks like. Yeah. Yeah, I'm thinking this isn't really. Yeah, I think this is a goofball. Well, that's interesting. I don't know why that one's. Oh, draw the logic diagram for this one. Oh, well, this one was actually hard to do the simplification. Okay, but you didn't have to do the SOP to POS conversion with that problem. I should have read the problem better. I just had to draw the logic diagram. Okay, well, the logic diagram, first I have to multiply this out, and then I just have an AND gate here, an AND gate here, an AND gate here, an AND gate here, and all of those go into an OR gate. And that's my logic diagram, okay? And these are they just come in here. But I'm gonna put this in pure form. I want to look at this, so hang on. Okay, so anyway, I did work this out because it drove me crazy. But remember, I didn't really give you this as a conversion problem. It turns out this one was really hard. And the correct answer then, it comes out to this. And the way you do it, it's a little tricky, but you go ahead and do this part, and then you have to multiply it out, and then you can simplify it. And when you're all said and done, you get Z plus W quantity times Z plus X quantity times Z plus Y quantity times X plus Y plus W. And I verified it. I verified it with a K-map. So it's all good, but oh my God, it's a hard one. And that's probably a level 3. All right, so anyway, don't worry about that. I'm not going to ask anything that bad. Okay. All right. So remember, you're just supposed to draw the logic diagram and not do conversion. And okay. And I even messed this up because it says make sure to get 3 layers. Well, I didn't do 3 layers. So let's go back and get this right. I swear. Amazing. Okay, one more time. I swear. Okay, so I'm going to copy that. Let's see. Here we go. Yeah. Okay, something like this. Okay, so it's X plus Y. I think I'm beating the horse to death. X plus Y. Quantity times Z times Z. I did the same thing again. Driving me crazy. X plus Y times Z plus WXY plus ZW. Okay, so AND gate, but this is an OR gate, and then it goes into an AND gate, and then all these go into one big OR gate. So the Z goes in separately, and then this goes in here, here, and here. So we have so this is one layer. So you have intro layer, middle layer, and output layer. So layer 1, 2, and 3. So you do get 3 layers because you have to have this gate. I should have written it better. So you have the OR gate here, and it goes into an AND gate, and then you have 2 more AND gates. Well, I didn't leave room. So, so this is X and Y. This is Z. They go in here, and then this is WXY, and this is ZW, and then they all go into this final output OR gate. Okay, so that's what it should look like. So you do have to get 3 layers. So first layer, just this OR gate. Next layer, these 3 AND gates, and the next layer this 1 output OR gate. So the X variable has to go through 1 gate, 2 gates, 3 gates before it gets to F. So you do have 3 gate delays. So is the Y variable. The Z variable doesn't. Neither does the XY, the WXY, or the ZW. But you have an X and a Y here, so you're going to have to wait on that. And that can cause problems if these are the band if the clock width is pretty narrow. This can get you into trouble because this X is going to get to this gate slightly later than this X gets to this gate, and same with the Y. All right, so that's why we try and avoid these things if we can, and sometimes we have to put buffers in here in order to make all these gates spit out their answers at the same time, so we don't have false readings and hazards. Okay, I'm going to finish this up. We're at 40 minutes, and I want to get this done, but we got a couple more to do. Okay, all right. So convert the POS form. So we have A B prime C prime plus A prime B prime C plus A B prime C prime. All right, so what are we going to do with this? Well, the first thing is, notice we have an A B prime C prime and an A B prime C prime. So that's redundant. So we don't need that. So we're going to get rid of one of these terms. And that leaves us with an, so let me write this. I'll write it out because I don't know if you can see the cursor. Sometimes the cursor shows up, but sometimes it doesn't. Which is really hard to understand why that is, but it is the case. All right, A, B prime, C plus A prime, B prime, C. Oh, it's a C prime. A prime, B prime, C plus A, B prime, C prime plus A, B prime, C prime equals F. All right, so we want to go to POS form. It's in SOP form. All right, so all right, so can we combine any terms? A, B prime, C prime, A, B prime, C prime. Yeah, so that appears twice. So we can just get rid of one of these terms. That leaves us with A prime, B prime, C and A, B prime, C prime. Now can we combine these? No, we can't. But we can use the M and F with the A prime, or we could use the B prime and do the second distributive law, or we could use C prime and do M and F. So we have a bunch of choices here. So let's do A prime and do M and F. So we get A prime plus B prime C prime quantity times A plus B prime C. So that gives us that, and then we have to expand these using the second distributive law. So that gives us A prime plus B prime quantity times A prime plus C prime quantity times A plus B prime quantity times A plus C. So that's one solution. Now that is in POS form. Let's do it another way. So instead of using the A prime and doing, let's take out the B prime and do second distributive. So we would have B prime plus A prime C times A C prime. And okay, and then now we can use now we can use the M and F or C3, and that's going to give us A prime plus C prime quantity. No, let's see. So this let's see. Yeah, no, this should be. Yeah, we should be able just to put those all together. And if we do that, that gets weird. Let's see. Yeah, if we do that, yeah, I think there's a mistake there. Yeah. So we have. Let's just start this over. So we'll start over. We have A prime, B prime, C plus A, B prime, C prime. So let's factor out the B prime. B prime times, that's what I did wrong, A prime C plus A C prime. Okay, so yeah, I shouldn't use the second distributive law there. I should factor out the B. And then now we have to use the M and F on this. So it's going to be B prime times A prime plus C prime quantity times A plus C. Now that's in POS form. So that's quite different than what we got there. Interesting. So, hang on. Let me see what the correct answer is. Yeah. So I made a mistake here. This one is correct. This is the right answer here. B prime times A prime plus C, quantity times A plus C. Same thing down here. And I had to use a K-map just to check it. I did make a mistake here. This was totally wrong. But this was right. All right. So anyway, those were really hard problems. I'm surprised I gave those on that test. When was it? September 18, 2017. Yeah, I feel sorry for this class. Those were hard. Those were some hard conversions, actually. Trickier than normal. Not impossible. I mean, I made a little mistake. It's doable, but this one, I didn't actually ask them to convert it, but that was really difficult. That was a lot harder than I thought. And some of them are really hard, and I wouldn't expect you to be able to do this. I think probably in the whole class, maybe 1 or 2 students would get it right, and maybe nobody. So it was hard. All right. ASCII character C takes up 7 bits. True. Fonts are usually multiple bytes. Some do not scale very well. That's right. TrueType and PostScript scale fine because they're made out of glyphs, but any other kind of font won't scale, or at least I guess as a general rule. Often when we write a truth table, there is ambiguity in the resultant circuit. There is no ambiguity in the truth table, but when we have English statements, there can be ambiguity. What's the output for a 3-input gate? What's the output for a 3-input AND gate when the inputs are 1, 1, 0? Okay, well, we have a 0, so the output's a 0. Remember, for an AND gate, all inputs have to be 1 to get a 1 out. Write a Boolean equation for this sentence. Use variables like the Spurs will beat Golden State if their players stay healthy and they play with focus or get lucky, or Golden State has a bad game and doesn't shoot well. Yeah, so we said H for healthy, F for focus, L for lucky, R, G for Golden State has a bad game, and S, Golden State doesn't shoot well. So how do we do this? Well, so so probably the way to set this up would be that we would just do, so we would do healthy, healthy, focus, or lucky, or bad game and doesn't shoot well. So that would be one way to do it. But you could also say you could put parentheses in here, and you could put parentheses here like this, and you could say, so if the Spurs stay healthy and play with focus or get lucky, or Golden State has a bad game and doesn't shoot well. That might make more sense. So there are several different ways to interpret that, and how you interpret it does change the truth table. Ambiguity is easy to creep in, so that's the whole point of this. All right, so we're going to finish this up. So here we have an AND gate, and sometimes we put the dot in there, usually not, but anyway, it just means AND. Notice we have an inverter in the output, so it's actually a NAND gate. And then we have inverters in the A and B. So the way to think about this is an AND gate before the inverter only generates a 1 if all 3 inputs are 1. So the A has to be a 0, the B has to be a 1, the C has to be a 0. So in order to get a 1 before the bubble and a 0 after. So that would be 0, 1, 0. 0, 1, 0 is this line. So right there, we would get a 0. And everywhere else, we're going to get a 1 because of the inverter. And then the minterms then are going to be 0. The minterms are going to be 0, 1, 3, 4, 5, 6, and 7. So that's that. All right. And then if POS, so we've got some more. Hopefully these are easy. Okay, D. So this one goes, and we have AC plus BC. So that's pretty easy. So let's do this one. So that one actually is easy. So let me switch over here, and we will do that one. Okay, so, all right. So we have AC plus BC, A plus C times B plus C times A plus D times D. Okay, so this goes immediately because we have an AD and a D here. And here we have an AC and a BC. So we can write this C plus BC times D. We can distribute the D in, and we just get CD plus BCD. And that's it. All right, pretty easy. And then this one down here, where we have W plus X prime times W plus X times W plus Z prime. That's just the corollary to the second distributive law, where we have X plus WYZ. So let's copy that down. So W plus X prime quantity times W plus Y quantity times W plus Z prime. Okay, remember we had X plus WYZ just equals the quantity X plus W times the quantity X plus Y times the quantity X plus Z. Okay? So, and so this is what we have. We're going to apply it in this direction. So it's really pretty easy. So this is just going to be W plus X prime Y Z prime. That's SOP. That's POS. All right. And then the last one is A prime B plus A prime C. And that's really easy. We're just going to factor out the A prime. And that's going to give us A prime times B plus C. And that's POS form. All right. And then, we do have this two terms. I'm not going to, I want to do this adder thing. Well, okay, let's look at this. So this is actually pretty easy. So let's write it. So our expression, we have minterm 0, 1, and 3, plus or minus minterm 2, because it's a don't care. So let's write this. All right. So we have ABC, f of ABC, with the don't care equal to 0. We have minterm then 0, 1, and 3. So that's going to be A prime, B prime, C prime, plus, that's 0, plus 1, A prime, B prime, C, plus 3, A prime, B, C. And then we would add, so we combine these, so these two can combine A prime, B prime, and these two can combine into A prime, C. And that's all you get. Remember, you can use them twice, so we use that one twice, that's fine. Now if we add the final term, so we have A prime, B prime, C prime, plus A prime, B prime, C, plus A prime, B, C, plus the minterm 0, 1, 2, which would be A prime, B, C prime. So this is minterm 0, 1, 3, and there's 2. So these two can combine to A prime, B, because the C drops. This can combine to A prime, B prime. So now we've used 1, 2, 3, 4. We've used all 4 of them. So now we can combine these two into A prime, and the B drops. A prime, B prime here, A prime, B there. So we just wind up with A prime. Much simpler than this, so we want to pick it with our don't care equal to 1. And then let's do the final one, where we're going to look at this. Hopefully you saw that. Let me go back, make sure that was all on the screen. Not quite. Okay. So we took A prime, B prime, C prime, plus A prime, B prime, C, combined those to A prime, B prime, and then A prime, B prime, C, and A prime, B, C prime to A prime, B. A prime, B prime, and A prime, B combine to A prime. The B drops. And that's much simpler than this. Okay? All right. And finally we're going to look at the last one here, the adder. And so I'm just going to do this part. So we want to fill in these rows. It's simple. We just do the math. We add 4 bits of A to 4 bits of B plus 1 bit of carry in, and that gives us 4 bits of sum and a carry out. So let's do it. So the first one is A. The 4 bits of A are 1100, 1100, and then the 4 bits of B are 1100, 1100, and the carry in is 1. So that adds up 1, 0. 1 plus 1 is 0, carrier 1. 1 plus 1 plus 1 is 1, carrier 1. So our carry out is 1, and our 4 bits of sum are 1001. To do the other one, 11110 for A, 1110 for A, and then 0111 for B, 0111 for B, and a 0 for the carry in. So that's just 1, 0 carrier 1, 1 carrier 1, 0 carrier 1. So that's just a carry of 1 and 0101. And then if we want to make, so we just add those up. 1100 and 1100 plus 1. So this is A, that's B, that's the carry in, and that's what we get. This is A, this is B, and that's the carry in, so that's what we get. And then if we want to subtract B from A, and assuming that these values will fit in, their 4-bit values will fit into 2's complement into 4 bits, where remember -8 and +7 are our smallest and biggest numbers. So assuming that's true, then to subtract B from A, all we have to do is invert all the B inputs and make the carry in a 1. And that's inverting all the bits and adding 1. And that makes B 2's complement negative number, and then we do the addition, and we get the difference between A minus B. Again, we have to assume, though, that they fit. Okay, and I think that's all I want to cover here. So let me. I think I'll do 11 p.m. Thursday night. I'll do a thing. I'll send out an email, and hopefully I'll answer questions, and hopefully you guys will be ready to go. I will try and stream the 11 to 11:50 lecture on Friday, and I'll try and send out a link once I figure out how to do that. I probably won't send the link out till right before class starts at 11, because I'm not sure how to generate that link in the classroom. So we'll see, and it may not work. And if it doesn't work, don't panic. But yeah. Okay. Yeah. Well, I think that's it. So hopefully this was helpful. We did 58 minutes, a little longer than I wanted to go. So I'm going to stop this, and I think if you review it, hopefully this will be helpful. Sorry for, I didn't realize this test had some really hard problems in it. And I knew there was one out there that had these, and I totally forgot. Boy, I feel sorry. A couple of these were tricky, I guess. Yeah, that one was a little bit tricky, I think. I don't know, one or two of them. Most of them weren't that bad, though. But yeah, this one I think was hard. Maybe that one wasn't. I don't know. But this was crazy, even though all you had to do for this one is draw the logic diagram. Sorry, you're not seeing it. It just drives me crazy. Here. Yeah. This one was crazy. But you just had to draw the logic diagram and get 3 layers. So you didn't even have to multiply, distribute the z in here, because that would have made it a 2-layer problem, which is what we normally want. But in this case, I ask you to do 3 layers. All right. So that was a tricky test. All right. We'll finish with we'll finish with that. All right, and then we'll do the test on Friday, starting at 10. Starting at noon. All right, and that'll do it.